I'm going to start the webinar with the objectives of our webinar. And previously a lot of our webinars have covered, my colleague Peter has covered in the webinars, the programs stated below: Slope, Pdisp, XDisp and GSA Raft. So our previous webinars have shown how the programs can be set up and their ease of use. So I didn't want to repeat that too much today. And you can refer to those webinars to get that information. So today I want the attendees really to appreciate the analysis methodology behind the programs and understand the capabilities of the programs through case studies and demonstrations. So I am going to start today with Slope, and Slope analyzes the stability of slopes and can be used to analyze, can also be used to analyze earth pressure problems and bearing capacity problems. It is a limit equilibrium analysis of circular and non-circular slip surfaces, and it involves it can also allow for the analysis of reinforcing elements such as rock bolts, soil nails, ground anchors and geotextiles. And it allows for the analysis of both soil and rock slopes. So the analysis methods are basically based on the method of slices. So all the Swedish, the Bishops and the Jambu methods, all methods of slices. The Swedish method deals with circular slips, and it's generally not used for submerged slopes or horizontal forces. Both Bishops and Jambu's deals with horizontal interslice forces, parallel inclined interslice forces, and variably inclined interslice forces. But Bishops is generally applicable to circular slips, and it's used where there's reinforcement, whereas Jambu is applicable to non-circular slips. So it really depends on the type of problem you're analyzing, what kind of analysis method you'll use. So I'm just going to briefly cover the inputs, and I'll start with the stratigraphy. The stratigraphy can be inputted either through the tabular input section or graphically, and you're able to vary cohesion with depth. With your groundwater profile, you can be inputted as hydrostatic. It can be a varying groundwater profile. You can put the piezometric values in, or you can even put your RU values in. And there are a number of reinforcement options, as I previously mentioned, and we'll touch upon in the case studies which are coming up. And in terms of forces, you can have surcharge loads at the back of or along your slope, and you've got horizontal and ground acceleration, a horizontal ground acceleration option for force as well. So to understand the analysis, it's quite useful to look at the output. So the output for slope is tabular and graphical. For the graphical output, it initially chooses your worst case slope. So if you look down to the right hand corner of your of the presentation, you'll notice that we've got a factor of safety there of 1. Now this is probably the worst case for this specific problem. You could choose a higher factor of safety slip and show it in your graphical interface if that's of interest to you or useful to you. Slope also gives much more detailed information, so it gives each slip circle's x and y coordinates, radius, slip weight, factor of safety, disturbing moment and restoring moment. And all of this information is available in the tabular output, which can be exported into Excel and analyzed appropriately if you want all that detailed information. But I think to appreciate what Slope does, it's really nice to see how it's used. And I've got some case studies that Arup have sent, and I'll start off with the A465 Heads of the Valley Trunk Road in Wales. Now, this is one of the simpler analyses that have been set up. Arup were required to check the stability of a reinforcement wall along a critical section of the proposed alignment, and they had to review the potential rotational failures beneath the reinforced soil block. So Oasys slope was used for the analysis. So analyses have been carried out using the Bishop's method with variably inclined interslice forces. And the circular slips have been defined by a common point through which the circle passes. Now that common point is at the back corner of the reinforced soil block. So what I'll do is I'll take you into the actual analysis file for this job. And if you look here, you can see the title screen. So you can see we've got the details here, the person who set it up, details of the specific problem, If you go to analysis options, as I mentioned, we've chosen bishops and variably inclined interslice forces. Of interest to a lot of people might be the partial factors section. This was designed to the British standards, but you can also design here to EC7, so design approach 1, combination 1 and 2 integrated into here. And of course there's the material properties, which are put in here for fill reinforced soil, which represents our reinforced soil block, and glacial till. We've got a groundwater profile which has been set in. It's variable, and for each strata we can give information about the pore pressure distribution, and we can also give the actual details of the strata either through a tabular input, as is shown here, or through the graphical input. So for example, I could just go down here, add a new stratum, and just put it in. And as you can see, as I move my cursor around at the top left-hand corner, you can actually see what your coordinates are. So if I just go, and as you can see, we've applied 2 surface loads here as well. So if I just go to graphical output, this will help you appreciate what slope does now. After I've run an analysis, it just chooses the worst case slip surface through the common point that I mentioned. So the slip surface was selected to go through a common point, which is the same coordinate as the back of the reinforced soil block. So it's 32, x equals 32 and y equals 9.9. So there you go. You can see that the lowest factor of safety is 0.917 here. And that's a worst case, and it's quite low, so we'll probably have to redesign in that case. So that's pretty much the way analysis is run and how it works. If I go back to the presentation now, I'll move on to our next case study. And this case study covers Black Creek in Australia. In this case, Arup was appointed to provide the geotechnical investigations and designs as part of a larger Northern Railway project in Australia. The analysis was required for a reinforced wall bridge abutment, and Arup had to carry out the global stability check of a reinforced wall bridge abutment. So as you can see, the bridge abutment is shown here in the circles, and the reinforced wall parameters are shown here, so you can appreciate what's going on there. So the reinforced wall was represented by multiple geotextile reinforcements, and as you can see here, this is the reinforcement section in slope. So we've chosen geotextiles, we've chosen various levels, and I've clicked on the multiple here, and the length is shown at the top and the bottom layer, which is constant. So this is shown here in the slope graphical output. And as you can see the multiple geotextiles shown, and the spacing is 0.3 meters as is entered in there. And as you can see at the top of the graphical input, we've got an acceptable factor of safety of 1.761. So I'm now going to move on to our final case study in slope. This is a geotechnically very interesting case study, and it was done in Hong Kong. Arup were commissioned by the government to carry out a study to evaluate the stability of a slope which has a history of instability problems. Now, if I give you details of the slope, it's located in a densely populated area. It's 36 meters high and 187 meters long, with a 6 meter high caisson wall at the slope toe. And it has actually had problems before. It's had several landslides in the past, and soil nails were installed in the early 1990s, and Arup had to collect historical data for that. So on the basis of that, I'll show you the existing slopes. So as you can see the historical landslides, which are shown in the slide here. You can also see Arup's representation after collecting historical data of the soil nails along the slope. Now, Arup modelled the existing wall. Using Oasys slope. The existing soil nails were modelled using the reinforcement function, and the minimum factor of safety was found to be 1.2, which was below the required factor of safety of 1.4. So Arup had to propose a new slope, and they did a slope analysis on this as well. And so they proposed to the client to install additional soil nails to improve the overall stability of the slope, and this was analysed using slope. And upgrading works were completed in October 2010. So if you look at the picture below, you can see where the soil nails have been installed, and it was a very interesting job. So now I'm going to move on to our other soil movement software, and I'm going to start here with XDisp, which looks at the ground movement caused by excavation. So XDisp calculates ground movements at and below the surface, and it can be used for a number of different types of projects. So for example, where you've got tunnel excavations in soft ground, where you've got circular shafts, retained cuts, or mined excavations. And this depiction here to your right hand side will show you, for example, if you excavate a tunnel, you can pick a specific point. Say you're interested in point 8 here. You can see what kind of movements are happening in the X and Y direction there. And even with this excavation, again in point A, you can find out what movements are going on there, or below the surface if you've got a subsurface curve. So now I'm going to look into the analysis method in more detail. Different theory is used for different types of excavation. And so I'm going to start with tunnels. And for tunnels, the movements are generated from normal or Gaussian distribution curves, and the distribution relationship is empirically based, so it shows a close match to tunnel-induced case study movements. This match is actually this is an interesting point in that the match can actually be difficult to achieve using FE, and here I'm referring to the Addenbrooke and Potts study done at St James's Park, which is I think described in Syria 2001. It's also interesting to note that XDisp considers a 3D problem. So say you have a tunnel, you have a different number of excavations in different areas happening at different levels. It can consider all these and accumulate the results together. So in that way, it's a very different kind of analysis that you would get from a 2D FE analysis, which couldn't do all those things. So for the inputs, interestingly, you don't have to consider soil properties because it's not analytically based. So really, we're looking at an empirical analysis, and we're looking at parameters of importance such as volume loss and trough width parameter. Now these are the two key parameters, and the way you would derive this for your soils is really given in detail in our manual, which is available as a PDF on the website. So once you have these two parameters, you can actually plot the complete three-dimensional behavior of the ground due to tunneling. So it's actually quite an interesting feature, and I'm just going to go on now to the theory behind mined excavations. I'm just going to touch on this because, as I said, there's quite a lot of detail in the manual about it. But really, it's based on the theory proposed by Wren et al., and it covers the surface movements caused by mine excavations and requires a user to enter influence factors. Now, details of inputting influence factors in the theory are given in the manual. So I'm going to cover another type of excavation that XDisp analyzes, and that is embedded walls. For embedded wall excavation, surface displacements are given from curves based on empirical data. Now, XDisp already has inputted the Syria C580 curves, which consider stiff clay and sand. But it's often the case that the user might be interested in another type of soil, and the user is able to input their own curves from site data or empirical data of their own. So the method is really applicable to any type of stratigraphy as long as you have some good empirical data, and there are a lot of papers available out there for that. So XDisp is also proved very handy and well used for the reason of building damage assessments. It's very useful for projects which are done in densely populated areas, and it looks at the surface movements that are calculated in XDisp and assesses the effects of these on the building. So once you've entered the building's geometry, and it pretty much treats the building as an elastic beam element, it associates a damage category to your building based on Berland and Berland's damage categories, which go from negligible to very severe. And it looks at, for example, the crack widths and tensile strains that come out of your building, and it associates a category of damage to your building based on that. So I'll touch upon the inputs because it's really been covered quite well in the theory. But there are two types of problems which can be covered, the mining problem or the tunneling and excavation problem. So you've got to assign what problem you have. You've got to assign the points that you're interested in. Maybe you're interested in a tunnel, so you might want to put a displacement line in. Maybe you just want to know the displacements at the surface generally, so you put a displacement grid in. Or maybe you're just interested in one specific point, so you can put a displacement point in. You also need to input the geometry for your tunnels, walls, mines and buildings, and put the properties appropriately in there. So we'll come to the outputs from Pdisp, and the outputs have actually been developed extensively for inclusions in reports. So as you can see, you have a nice 3D output. You can map the contours of displacements based on your 3D outputs. You can actually show your 3D displacements, which are shown in your bottom right-hand corner. At the top left-hand corner, you can, along a line, you can pick up the line and plot your line displacements. Or with the building damage interaction chart, you can see how your building fits in to the building damage category, and it's quite handy to show clients, for example. So XDisp has also been recently developed due to extensive use on urban tunneling projects. And so, for example, initially we had no corner stiffening. So where you've got this red circle here, at the top, there's no corner stiffening shown. So if you have any kind of utility or building near there, it might overestimate the displacements you would have at the surface. But now, from a paper produced by Fuentes and Devrand, we've got corner stiffening incorporated, which produces more accurate results, and will give you something less conservative and hopefully more helpful. Subsurface modelling is also something which XDisp did according to Series C580. And what Series C580 assumes is that at the surface you have your displacement, and at the bottom of your excavation you have zero displacement. So it just linearly extrapolates your displacement down to zero. Now, if we look at empirical data which has been taken, a great deal of empirical data shows that this is actually not accurate, and that it's not realistic, as soil moves around the base, and you do have soil movement around the base. So we've actually put a new feature in, which is the subsurface movement curves, which allows the user to input subsurface movement curves so that they can get more realistic movement. So if you look at the bottom of the excavation at the top, you've got zero movement. If you look at the bottom of the excavation at the bottom, you have quite a high movement. So this plots a much more realistic amount of movement. And say, for example, you had a utility close by, this gives much more accurate information. Now, a point to note is that the subsurface curve really can be created quite easily by looking at movements away from a single excavation, either, for example, from site data or from a 2D or 3D FE analysis. And so once you've got that information for the single excavation, you can apply it to your XDisp problem and plot a number of excavations near your site or around your site. So in that way, it's quite a useful tool. I think it would be nice to show you a model and show you how it works. So I'm just going to move on now to a quick demo. Okay. So here we go. Here we've got an example in XDisp where we put a tunnel next to an excavation, and here the problem type is a tunneling or embedded wall excavation. We've put our displacement data in, so I'm interested in a grid which is at the surface of the problem, and a number of lines, maybe associating with the tunnels, maybe associating with utilities close by. And as you can see, the tunnel data is shown here. We have the geometry of the tunnel, and we have, as you can see, there's one endpoint and two endpoints here, but you can have a number of endpoints if you prefer. And there's the analysis parameters here. So I said the volume loss, the K parameters are all in there. The embedded wall excavations are also of interest. So we can have circular excavations as shafts. We've got the installation. We've got the initial excavation installation of a wall, and you associate here. We've associated the Syria C580 curves to it. So there you go. We've got the installation of a planar diaphragm wall in stiff clay. We have a number of options. We could choose from Series C580, or if you're not using Series C580, you can actually have put a new curve in there based on your site data or empirical data from papers. But if we just have a look, at one of these graphs, we can see that it's just a look up from the Series C580 graph here. So you can have a look at the Series C580 graphs as well. So we'll go on to the outputs, and if you have a look here, here's my contoured output. I've got the excavation here and the tunnel details in there. If I take the contours out, I can actually pick a line. Say I'm interested in the line which goes along the tunnel. I can see the impact of the excavation and the tunnel construction here. And we can even go into the 3D graphics and see how in 3D our problem relates to what's going on. So you can see in 3D how the movement is occurring caused by the tunnel and by the excavation. So that gives you a good appreciation of what's going on. I'm going to now go on to our other soil displacement software, which is Pdisp, and this is soil displacements due to pressure. So Pdisp calculates displacements due to the application of a pressure, either due to loading or unloading. And examples of Pdisp analysis include predicting settlement of ground due to surcharging, predicting settlement of flexible footings or rafts, predicting settlements of tunnels due to loading or the unloading of soil. And if we look at the analysis methodology for Pdisp, Pdisp uses the Boussinesq method, which gives us stresses and displacements in soil. And it gives us the Mindlin method, which gives displacements only, but can also deal with shear. So if we look at a comparison of the two methods, we can see that each of them have their strengths and weaknesses, and both of them give vertical displacements and vertical normal pressures on a horizontal plane. But Mindlin deals with horizontal displacements as well and traction forces, so it's good with shear. And Boussinesq deals with soil nonlinearity and stress changes. So obviously if you want to find out more about your stress, you would apply the Boussinesq methodology. So it really depends on, again, on the type of problem you use as the type of analysis you will undertake. And if we look at the Pdisp inputs, we can appreciate what it does. So as with XDisp, you're able to calculate the displacements at a point, along a line or a grid. It deals with rectangular and circular loads, and these loads can be applied at an angle because Pdisp now deals with horizontal forces. And it's able to prescribe multiple soil profiles and plan. So when I say this, for example, if you had a soil lens, if you had a patch of rough made ground or something along those lines, for those kind of cases you can apply it by applying a soil zone and plan. So just to appreciate the idea of soil zones and to understand how Pdisp inputs information, you can see that you can have variable E values, and you can see in plan that these two soils are very different, and you can apply soil zones like that. Also with Pdisp, as I've mentioned, you can have a look at the different types of loading, and these loads are rotated, they're not necessarily to the vertical, and as you can see they're rectangular and circular. So with the Pdisp outputs, Pdisp has an extensive graphical output options, again to help you with reports really, and it's developed for that reason. So the graphical outputs include contouring and graphs, and the tabular outputs give really detailed results of displacement and stresses at points defined by the user. So I think it would be really nice to go into a Pdisp model just to familiarize you with the interface if you're not so familiar. Just going to go in here. Okay, so as you can see, with the analysis options, you have the option of Mindlin or Boussinesq. You have a number of soil profiles you can set, and the Young's modulus can either be constant by setting the same at the top and the bottom, or varied. We've got the soil zones in plan, the load data, which is rectangular or circular. We've got our displacement data, which is just what we're interested really in. We've got some grids here, lines here, and points here. And we've got an input section where you can graphically input the information. So as well as, say for example, typing in your soil zones according to your X and Y coordinates, instead you could input them. So you can input your loads, your displacements and your soil zones into the graphical input section in here. But if we go to our output, as I previously mentioned, you can pick up, for example, a line displacement if you're particularly interested. And for example, along that line, you can pick say for example, I wanted the highest point. As you can see, right in my screen, I'm showing the ordinate here of 102.65. So that's pretty much our maximum displacement. And I know that aligns with 16.1 meters along my specific line. But alternatively, I can go to the tabular output and pick that up. So if I look at the 3D graphics view, as you can see here, we can appreciate what's going on with the different soil zones, and we've got the contouring shown. We can get the soil column displacement. So for a column of soil, say at 0 meters in our problem, we can get the displacements along, and it gives again details of the displacements. And you can get your tabular output. So if I select everything, and this again is exported into Excel as with XDisp. If I go down here, so you can see I've got the outputs, and for the grids, if I was interested in a specific point, I've got the X, Y, and Z details, the stresses, because this is Booz-Nesk analysis, and so on and so forth. So it's a very powerful tool to help you with displacements. Now I'm going to go into a case study with Pdisp. Now, as with most of our use in with most of our clients' use, both with Arup and external clients on Pdisp, Pdisp deals with displacements, so projects are often quite sensitive in nature. So for that reason, we don't have named case studies, and even this case study, I'm not able to mention the details of the study or the location. But it's a nice study in that it compares Pdisp to a 3D FE analysis and shows how the results compare for the two. So this is a study undertaken by Arup, and here Arup was responsible for designing a building in London directly above the LUL tunnels. So in this case, for the preliminary problem, they did a 3D FE analysis, which was used to model the building in the piles. So they really wanted to also model things like soil structure interaction. But they were required to do a category 2 check, and this had to be undertaken using separate software, and this software that was used was in the form of Oasys Pdisp. So Oasys Pdisp was used to analyze the same scenario, and this is just a look at the output from Oasys Pdisp. So as you can see here, following a number of different loads, we've got a grid at the surface, and we've got two lines which are the same as the crown of the tunnels. And as you can see, also in the Oasys Pdisp model, you can appreciate the 3D movement of the grid and the 3D and the movement along the line as well. So it helps you understand which loads are the most onerous and where your movements are occurring and how. So if we go on to the comparison, here on your left-hand corner, you'll see the LSDyna outputs, and on the right, on your right hand, you'll see the outputs from Pdisp. So as you can see on the left hand, the peak change in stress at the crown of the tunnel is 68 kPa, and this corresponds very well. In fact, it's the same as Pdisp, which is also 68 kPa. And it's interesting to note with these two problems that the peak movement occurs in the same area, and patterns of movement are also occurring in the same area. So this is very comforting and quite good verification of Pdisp. The vertical displacements were also compared. So this is a Booz-Nesk analysis which looks at stresses and displacements. And the vertical ground movement from LSDyna was 3.18 millimeters. Now this is actually lower than the Pdisp peak ground movement, which was 6 millimeters. And as you would expect anyway, Pdisp is based on more conservative analysis, so it will give a more conservative result. But there is a reason for this difference, and that's because Pdisp doesn't model the structural stiffness of the foundations, tunnels, and walls, which LSDyna does. So this is something that we have realized, and this is something that we're going to cover in our next piece of software, GSA Raft. But it's interesting to note with this actually that 3.18 and 6 millimeters are coming close, and also that the trends of movement are similar. So again, where the peak displacement occurs, the peak displacement occurs in LSDyna. Where displacement starts to ramp up, it's the same in LSDyna. So so again, this is a very good verification of the Pdisp and its methodology. So I'll go on to the Pdisp developments. Recently, Pdisp has been developed to consider horizontal displacements and forces and traction forces. There's also something that our developers are currently working on, and that is to connect Pdisp and XDisp. So for example, where you have a problem where you're constructing a tunnel, you're putting numerous excavations above the tunnel, but at the same time you're maybe demolishing a building close by or applying a load, you want to do an XDisp analysis for the tunnel and the excavation and a Pdisp analysis for the load. But can you marry these up? Well, in short, yes you can, because XDisp and Pdisp have the same input format for their displacement points, lines and grids. So all you do is you put the same displacement, say line or point or grid, into your XDisp model. You run your analysis as you would with a normal model, and you can export that data, and that data is it's now possible to import that data as a transferable file into Pdisp. Now in Pdisp, with your exported data already incorporated, you run your analysis as you normally would, say having an unloading because you've got a demolition there. You run it and you will have the overall soil displacements, say at your grid or at your point, caused by your overall problem. So as you can see, it becomes quite a powerful three-dimensional tool. And we've often been asked, why didn't you just combine this all into one big black box program? And the reason is that we really want you to also understand the kind of analysis that's going on behind the programs, and because they run on such different methodologies, that's the reason they've still been separated out. Another development touches upon what I mentioned in the case study, and that is that Pdisp doesn't deal with the soil structural interaction. So for that reason, GSA Raft was created, and with GSA Raft you've got the analysis of the soil structural interaction with the raft structure, so something like a basement slab, through a Pdisp and GSA link. Now, I'm just going to touch upon this today because GSA Raft is an extensive program, but what I'll do is I'll try and explain the methodology to you and show you a quick case study in GSA Raft. So GSA Raft is a program that looks at the non-linear soil structural interaction for piled and bearing foundations. It's a combination of GSA and Pdisp. You've got the soil structural interaction, so vertical for rafts and vertical and horizontal for piles. You've got a choice of methods, the Busenesque for rafts or the Mindlin for rafts and piles, and you've got an iterative process to consider. So if we look at the iterative process, initially you start with where GSA assumes a spring stiffness, and then GSA analyzes to get the soil pressures and displacements. This feeds into a Pdisp analysis of the spring forces to get soil settlements, and GSA calculates the new spring stiffness from forces and settlements. And you repeat again you repeat back to where GSA analyzes to get soil pressures and displacements. And this, once the Pdisp and GSA movements converged, you have a solution to your problem. So this is really what's going on under the bonnet, because what all you would do is you would just press the analysis and you would wait for it to converge. But it's nice for you to understand what's going on. And I've got here a schematic representation of the piled-raft model to further help you with your understanding. So as you can see, a load is applied here. You've got your raft at the top. You've got your pile, which is represented by a number of nodes. And as you can see, your soil here is represented as non-linear springs. So in the next slide, I've got this in much more detail. So for the non-linear soil springs, every node on the piles are connected by 3 non-linear springs to represent the soil non-linear behavior immediately around the piles in the X, Y, and Z directions. Now, these non-linear springs are then attached to the ground in the soil, and the soil is still considered as elastic media, so the settlements are still calculated using the Mindlin method. So that just touches upon how GSA works and GSA Raft works. So now I'm just going to go into another case study, which is King's Place. This is a case study of something that was done in London. And King's Place is a 3-story basement next to a canal, and it's got the basement construction with diaphragm walling, and the construction sequence includes, for example, temporary and permanent props. A raft was proposed as a cost-saving alternative. So in this case, they increased the design effort, but they did this in order to save on piles. So GSA Raft analysed the settlement and overall bearing pressure. It gave a representation of the slab curvature from GSA Raft, which is shown here. So this gives the slab curvature, which is the building shown at the bottom, which is the image shown at the bottom. And it was able to go on and calculate reinforcement. So that's just a very quick overview of GSA Raft, and I'm coming to the end of my presentation now. So really I covered 4 programs. I covered Slope, which gives the limit equilibrium analysis of circular and non-circular slip surfaces. I've covered XDisp, which calculates ground movements due to excavations. And XDisp is now going to link in with Pdisp, which calculates displacements due to the application of pressure either due to loading or unloading. And because Pdisp doesn't deal with soil structural interaction, GSA Raft was produced, which gives an analysis of soil structural interaction with raft structures through a Pdisp and GSA link. So you may be interested in these programs, you may want to understand more, and for these reasons, what would you do next? Well, there's a help file and manual which is available to download on our website. You can try some step-by-step examples which are in the manual. There are previous recordings of webinars which are very helpful. So there was one on soil movement and slope stability, there was one on slope stability and reinforcement, and there's one on soil structural interaction with GSA Raft. And these show, for example, how these programs can be set up as well, so it'll really help you understand the interface better. But there are more webinars to follow. And support. We've got a website, we've got a technical FAQ section, which answers a lot of questions that you might have. We've got online training movies which were very helpful and again help you appreciate the interface of the programs. Of course, email us and call us, get in touch with us and let us know how you're getting on, and we're happy to answer any questions or discuss anything really with you. So I think now that leaves me to pass on to Nigel for any questions. So thank you everyone for listening, and thank you very much for your time.